We are living at an exciting time in human history, a time when we have unprecedented access to the accumulated knowledge of our ancestors. Those brilliant philosophers, artists, and scientists who discovered important truths about the nature of the universe and the forces that control it. In this video, we'll use some of this knowledge and some simple equipment to make an important calculation, the total power output of the Sun. E equals mc squared is a mathematical description of the process that powers the Sun, nuclear fusion. Einstein's elegant formula tells us that a small amount of mass can be converted to a huge amount of energy. In this lab, we will make some direct measurements and actually calculate how much energy the Sun produces. Remarkably, we can do this using some very simple equipment, along with some help from the brilliant minds that came before us. The equipment needed to do this is basic: a glass or clear plastic container with a lid, a timer, a thermometer, a piece of aluminum, and a measuring cup. I've constructed a hinged carrier so that the equipment can easily be adjusted to various angles. The process is simple. We will use the Sun to heat a known mass of water over a period of time. Start constructing your equipment by cutting a piece of thick aluminum foil so that it fits across the diameter of the container. The foil used in aluminum cookie sheets is suitable for this. Paint one side of the foil black. Black is the best color to use for absorbing radiant energy. Start setting up your equipment by filling the container with a measured quantity of water. This container holds 200 milliliters. Install the aluminum piece into the container. Attach the lid and insert the thermometer. We call this completed piece of apparatus the collector. Leave the collector sitting in the shade until the water temperature has normalized. It should be close to air temperature. Leave a second collector sitting in the shade as a control. This control confirms that any temperature change in the main collector was due to radiant energy from the Sun. Once the temperature has normalized, sit the collector in sunlight. Adjust it so the Sun shines directly at the metal plate. I created an alignment tool. When the Sun shines through the front hole onto the center of the back plate, the collector is aligned with the Sun. To begin, start your timer and record the temperature. Our starting temperature is 25 degrees Celsius. Leave the collector undisturbed for 15 minutes. During this time, radiant energy from the Sun converts to thermal energy, raising the temperature of the water. This compressed video shows the temperature change for the first 5 minutes, a rise of 2 degrees. While we wait, let's discuss some features of this equipment. The black aluminum plate plays an important role in this process. It intercepts energy that may pass right through the water. The color black absorbs energy, and the aluminum has good thermal conductivity, meaning that it efficiently transfers thermal energy to the water. A simple experiment confirms the effect of the black metal plate. Place 2 identical water-filled containers in direct sunlight, one with a black metal plate, the other without. Record the temperature of each. Wait 15 minutes and record the temperature again. The equipment in this image produced a 4-degree advantage for the container with the metal plate. Back at the collector, the timer tells us that 15 minutes has passed. The temperature of the water is now 32 degrees Celsius. The start temperature was 25 degrees. The water temperature increased by 7 degrees. Our control, sitting in the shade, is still 25 degrees Celsius. We now have all the information we need to calculate how much energy the Sun sends to the Earth. First, we'll calculate how many joules of energy the water in our collector captured. Scientists have determined that it takes 4.2 joules of energy to raise the temperature of 1 gram of water by 1 degree Celsius. In our investigation, the collector held 200 milliliters of water. Because 1 milliliter of water has a mass of 1 gram, we have 200 grams of water. The change in temperature was 7 degrees Celsius. So total energy equals 200 grams times 7 degrees Celsius times 4.2 joules per gram per degree Celsius. This yields 5,880 joules. Our collector captured 5,880 joules of energy from the sun. Let's convert this to power. Power is the rate that energy is used or created at. The unit of power is the watt. Dividing change in energy by elapsed time produces a value for power. Time must be in seconds. Our collector operated for 15 minutes. That's 900 seconds. To determine power, we divide 5,880 joules by 900 seconds, giving a result of 6.5 watts. The sun was delivering power to our collector at a rate of 6.5 watts. Next, we are going to calculate how many watts per square meter this represents. To do this, we need to calculate the area of the aluminum plate. This is the area that intercepted the radiant energy. The metal plate I used measured 14 centimeters by 4.3 centimeters. Area equals length times width. Plugging in our numbers, we get an area of 60.2 square centimeters. Let's calculate how many watts is collected by 1 square centimeter. Watts per square centimeter equals 6.5 watts divided by 60.2 square centimeters. The rounded answer is 0.11 watts per square centimeter. Each square centimeter of a surface pointed at the sun is receiving 0.11 watts of power. Let's convert that to watts per square meter. 1 square meter measures 100 centimeters by 100 centimeters. Each square meter contains 10,000 square centimeters. So, multiplying 10,000 square centimeters times 0.11 watts per square centimeter tells us that our part of the planet is receiving 1,100 watts per square meter. Our crude equipment yielded a result surprisingly close to the accepted average value of 1,000 watts per square meter. If you've made it this far, let's calculate the total power output from the sun. According to our calculations, surfaces on the Earth perpendicular to the sun receive power at the rate of 1,100 watts per square meter. To calculate the total power output of the sun, we need to calculate the total surface area of a sphere with a radius equal to the distance between the Earth and the sun. Each square meter of the inner surface of that sphere is receiving 1,100 watts of power. The area of a sphere is 4 pi r squared. The distance between the Earth and the sun averages 149 billion meters. Plugging the numbers into our formula, the area of the sphere equals 4 times 3.14 times 149 times 10 to the 9th squared. Completing the calculation, we find the surface area of this sphere to be 2.8 times 10 to the 23rd square meters. According to our calculation, each square meter represents 1,100 watts of power. Total power from the sun becomes the area of the sphere times 1,100, yielding 3.1 times 10 to the 26 watts. An accepted value puts this number at 3.86 times 10 to the 26 watts. Considering how simple our equipment is, we have results that are surprisingly close to the accepted values. If we had made allowance for reflection from the atmosphere and other complications that affect results, we may have come closer. What we have accomplished here is remarkable. With some very simple equipment, we have calculated the power output of the sun. Of course, this was only possible because we live at a time when we can use thousands of years of accumulated human knowledge, the creative output of brilliant minds. If you'd like to take this further, try this. How much energy does the Earth receive from the sun each second? And, using E equals mc squared, calculate how much mass the sun converts to energy each second. For more science and technology projects and videos, visit our website, hylaroad.com.